In the last segment, we talked about the fact that not all molecules that have polar bonds are polar molecules. And you were alerted to go back to your handout and figure out polar molecule, not bond, polar molecule. Do you have an ep dipole on those 6 pages? And what I told you was only go up to the tetrahedron, no expanded octets. Now, in an effort to move these along, I've preloaded some of this stuff so we can try to get this particular unit done. All right, some generalities. Generally, but not always, if you have an oxygen or a nitrogen, fluorine or chlorine halogens, and you have something that's non-symmetrical or bent in some way, it's a pretty good bet that that molecule is going to be polar. Now, the question is, why do you care? Well, this is super important as you move forward, because what you're going to find is you're going to have biomolecules made of carbon that you want to be compatible with water. And water, as we saw, is decidedly polar. Okay, so what we need to recognize is that when we made ionic compounds, if we had a plus over here and a minus over here, they attracted. And so the same thing can happen if we have covalent compounds. Let's just say, for simplicity, we have these two. And this is a polar molecule, and this is a polar molecule. Okay? If you have charge here and charge here, they're going to want to attract in some way. So we want to look at attractive forces. And there are a variety of them. London dispersion forces, dipole-dipole forces, ion-dipole forces, and the like. But the most important one is the hydrogen bond. And this is the special attraction between a partial positive hydrogen and a partial negative neighbor. Okay, now this is hugely important, and if you don't remember anything about basic chemistry, please remember hydrogen bonding when you go on to your other science courses. But let's say, for example, you have molecule A that has a partial positive hydrogen. Okay, and then you have molecule B that has a partial negative of something else. Your pluses and minuses are going to want to attract. They're not going to be bonded for all eternity because we can pull them apart, but they're going to want to attract and travel around in life together, so to speak. Okay? So, what we have on the next page, and I've preloaded these for simplicity so we can try to get through this. If I want to see if water and ammonia will hydrogen bond, the first thing I have to do is draw the Lewis structures. So I've drawn them here. And then I would ask myself, once I put the polarity in, do I have a partial positive hydrogen and a partial negative neighbor? And the answer to that is yes. Partial positive hydrogen, partial negative neighbor. So these two will hydrogen bond together. This one, it's tempting to say that this will hydrogen bond. However, sodium chloride is ionic. So you don't get partial positives and partial negatives, you get ions. What happens with those ions is what we call solvation, that the ions are surrounded by the waters with the appropriate charge. So sodium is a plus, oxygen on the water is a negative. So there's an attraction here. Same thing with the chloride. The chloride is minus, so it will attract to the hydrogen part of the water. And you probably drew this multiple times if you took the Chem 110 with us, because we emphasize that in that course. Now this, while there are attractions, and the sodium chloride will mix with water, we know that from the solubility table, and the fact that by experience you put some salt in some water and it's going to dissolve. Nonetheless, that attraction is valid, but that's not a hydrogen bond. Over here, I try to put this carbon compound in water. This is polar, this is not polar. So what happens is instead of these attracting, the water will just attract to other waters. Okay? So this carbon compound won't mix, and it will go off into its own phase. So over here, what we're doing is we're taking this carbon compound and we're sticking an oxygen in there. Okay, so CH 1, 2, 3, 4, and we put the oxygen in. Okay, now hopefully you're pausing these videos or you will go back to these and put in your own Lewis structures, because if you can't do the Lewis structures, you can't determine whether they hydrogen bond or not. Okay, so make sure that you can do that. That's why we did 6 pages of these. Nonetheless, what we end up having is an attraction between a partial positive hydrogen and a partial negative neighbor, partial positive hydrogen, partial negative neighbor. So this one will hydrogen bond, and what allows that to happen is the fact that we added an electronegative element. So when you get to biochemistry or anatomy and physiology or microbiology or any of those, what you end up finding is that your carbon compounds will mix with water when you add electronegative elements. And that is a huge, 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 huge deal. All right, other properties have to do with the fact that if you have molecules that are tangled up together with these attractions, the more tightly they are attracted, the harder it will be to pull them apart. Okay, now use whatever analogy comes to mind. Okay, think about human relationships. The tighter you're attracted to somebody, the harder it is to separate. Okay, now with respect to chemistry, with our states of matter, when you have something that is solid, you have particles jam-packed together. You're going to put a little bit of energy into that. You're going to spread the molecules apart, okay? So your solid is going to be jam-packed like this. Your liquid is going to spread out a little bit. And then we're going to put more energy into it, and we're going to spread these molecules out as far as they can go, and we actually have to put them in containers. That's called a gas. Okay, so we put energy in to make the phase changes. We take energy out to go backwards. Okay, now boiling specifically means liquid to gas. Okay. And melting is solid to liquid, okay? So you're going to have an energy situation happening each time you change states of matter, okay? Now, with respect to the attractions, how are you going to go back and forth from solid to liquid, liquid to gas, and so forth when we're talking about functions of intermolecular attractions? Okay, the higher the intermolecular attraction, like the hydrogen bond, the harder it's going to be to separate. Okay, more difficult to separate. Okay, and therefore the higher the boiling point and the higher the melting point. Okay. The lower the intermolecular attractions, okay, so this molecule over here, if I can get it to not roll around, and this molecule over here have almost no attractions. This is so far apart, this particle practically leaves that particle alone. And therefore, if I want to continue to separate these, make them into a liquid or a gas, it's not going to take much effort at all because they're already separated. Okay, so the lower the intermolecular attraction, the lower the boiling point, the lower the melting point. Okay, so what this has to do with then is that you have to think through what the intermolecular attractions are and whether substances are going to have higher or lower melting points or boiling points. So I'm going to do this really, really fast, try to get this all in one video. Okay, so ammonia versus water. Okay, so if I'm going to have a solid or a liquid, I have to have more than one. And you have more than one anyway, and it should be obvious why. All right, This one, while they're both polar and they both hydrogen bond to their neighbor, the reality of it is that this one is more electronegative and has a stronger attraction. So water will have higher boiling points and melting points than this one. Over here, our CH4 has absolutely no attraction whatsoever to its neighboring CH4. There's no polarity, none whatsoever. So this one goes off into la-la land, that one goes into la-la land. Whereas if I put a chlorine on there, partial negative, partial positive, partial negative, partial positive, we'll start having attractions. Now these attractions are not hydrogen bonds, but there's still more attractions than that one. So these will come and want to be next to each other, which means it will be harder to take them apart. And therefore this one will have a higher boiling point and higher melting point than this one. Okay, and then last but not least, on this one over here, our nitrogen gas, there's no polarity there at all. Your nitrogen gas doesn't interact with other nitrogen gases. That's why our atmosphere is 72% nitrogen and it's in gaseous form. That one doesn't attract to that one. However, over here, with our carbon compound, okay, with our carbon compound, and I'm just leaving the hydrogens off for clarity, partial positive, partial negative, partial negative, partial positive, these will be attracted to each other through the hydrogen bond, okay, or any kind of attraction, but this is specifically a hydrogen bond. And therefore, dragging this molecule away from that molecule will be more difficult, and therefore this one will have higher boiling point, higher melting point. Okay, yay, I think we're done. Who cares? Again, the reason that we care is that we want to start mixing particles with water. Okay, the human body, give or take, is about 60% water, which means if you're going to be compatible, if you're going to be a nutrient that's absorbed, if you're going to be an electrolyte that causes an action potential, if you're going to be a pharmaceutical or a vitamin that you take that gets absorbed into the body, you have to be compatible with water. And it's based on this idea of polarity, where what's being dissolved and what's doing the dissolving are similar. We're going to come back to this in Unit 6 when we talk about like dissolves like. Okay, this is a huge, huge topic. And with that, hallelujah, yay, we are done with Unit 2.